Okay, so now we're going to focus on what will become the next part of the course. So we're basically done with the overview of Java portion. So you now have way more than enough information, of course, to complete the programming assignment 1 and 2. You will also hopefully have learned enough about Java so as we get into the bulk of the course, where we do a lot more interesting discussion of real examples, you'll be able to follow along with the Java features we're going to use. The next part of the course, which is really the bulk of the, or it's the beginning of the bulk of the course, starts to cover the Android development environment and runtime environment. Now, Android is a massive, humongoloid thing, and so the first part of the discussions will give you a gestalt view of what's going on with Android, and then we'll start zooming in, probably starting next week, with the specific things you'll have to be responsible for to write assignment number 3, which is going to involve Android programming. But for right now, these are just concepts you have to understand. So the purpose of this is to acquaint you with the key layers in the Android architecture. And it's also a good time to give a pitch for what we call full stack development. So many people in our field, sadly, are only aware of their one layer that they work on. This is particularly true for people who don't get a Vanderbilt education. They go off to some other place where they don't get the benefit of a deeper understanding of what happens at many different points along the stack. We're going to cover everything comprehensively by the time you're done as an undergrad or a grad student. This will give you an overview of the stacks of the Android software environment, but be aware that much of what I'm going to talk about here is also applicable elsewhere as well. You can find other information about this stuff here at this link. We're also going to be spending some time talking about concurrency and communication, because those are really the most, in my mind, the most interesting parts of modern systems, trying to understand how to take advantage of multi-core platforms, take advantage of networking. That's really where the money is. That's really where the excitement is. So that's what we're going to emphasize here. All right, so the first thing to remember is that Android is a layered environment. So what does that mean? Well, it basically means that we don't try to solve all the problems in one fell swoop, but instead we break things up into levels of abstraction. And each level, or layer as it's called, has a set of things it does well, and in many cases it does those things in a very standardized way. So when you understand some of the layers here, you'll not only understand how Android works, but you'll also understand how most other operating systems and higher level software, middleware, etc. Behaves today as well. So Android provides a layered stack for mobile devices, and at the very, very bottom, of course, are all the hardware things. So I have my trusty Android smartphone, which has a bunch of sensors in it, like an accelerometer and GPS, and it has Bluetooth, and it has Wi-Fi, and it has connectors for USB, power, and other kinds of devices. It's got a bunch of different multi-core processor type things in it for doing general computation, for doing DSP, radio kinds of stuff, for calls, and so on and so forth. So there's a whole pile of hardware in these ever more powerful and life companion-like devices. We're not going to talk about any of that. What we are going to start talking about, though, are the software parts. And at the very bottom of the software stack, but of course on top of the hardware, is the operating system. And you'll see that Android provides a variant of Linux, although it's been heavily customized for the world of mobile devices. Some of the things that it adds, we'll talk about later, things like high-performance inter-process communication, sophisticated power management, are important because of the way in which people use these things as phones, not just mobile computers. There's also a pile of things that we call the middleware infrastructure. Middleware, you can look at middleware in a lot of different ways. The easiest way is to look at middleware as being the layers of software that sit on top of the operating systems, but underneath the underlying applications. So in this particular case, there's a bunch of different things in the middleware infrastructure. There's a thing called the Hardware Abstraction Layer, which we'll talk about in a little bit more detail in a second. The Hardware Abstraction Layer basically tries to provide standard interfaces for otherwise inconsistent hardware devices you find in modern smartphones, like cameras and radios and those kinds of things, which you have not historically found in more traditional desktop or even laptop environments. There's a Java runtime environment, which has a couple of layers. It has a virtual machine layer, which provides you an instruction, a managed hosting environment for running Java bytecode. There's also a subset of the core Java libraries, so some of the things we've been talking about, like collections, for example. And then there's also a set of native C and C++ libraries that do all kinds of interesting things. In fact, a lot of the actual heavy lifting in Android is actually done in C and C++. And we'll talk a little bit later about why that is. You might think to yourself, why do they do that? Why do they have this heavy C and C++ layer in an environment that's programmed largely in Java? And we'll talk more about that. Then there's also a whole pile of middleware frameworks, which are things that nestle on top of the infrastructure. So this is the infrastructure middleware. These are the application framework layers of the middleware. And this is all the kind of stuff that's getting closer to what you're probably experiencing more as a user. So the graphical user interface, services for handling the telephony modes, cameras and other multimedia devices, so video playout, various kinds of multimedia frameworks, obviously music, iTunes-like stuff, and then all kinds of other things we'll talk about later. And also, how do you actually deliver applications to people? That's the part where there's a market for developers. And then the final thing that comes with an Android distribution are so-called packaged applications. And these are the apps, right? This is stuff like browsers and email and calendar and contacts and all that kind of good stuff. And Android ships with about 24 or so open source applications that come out of the box. Sometimes vendors will add more stuff on top of the ones that come from Google, but oftentimes they'll also keep the Google ones there as well. Now there's also non-packaged applications that people sometimes bundle, like Google Maps or Gmail or so on, or YouTube and so on. But those are typically not available in open source form. Although if you really want to hurt yourself, you can go to the trouble of decompiling the bytecode classes to try to see what those things look like. Anybody ever try to do that? Anybody take a look and decompiled Maps or Gmail or anything to see what the source code looks like? Well, if you ever want to amuse yourself, you should do it, because they are very careful and they shroud the code. So before they release the code in bytecode form, the engineers at Google run their programs through an obfuscator, and it replaces all the nice, long, user-friendly names that we're taught in school to write to make code easier to understand with like A, B, C. Right? So it completely obfuscates the code. So you have absolutely no idea what that code does. And they do that because that's sort of their intellectual property, and they don't want people to just steal it. All right, so that's basically a really quick, fast, 2-minute tour through the layers in Android. We will now go and talk about each of these layers in a little bit more detail. We'll first start by talking about the Android Linux kernel. And so you can find out more at this Wikipedia link about Android Linux. A lot of what's in Android Linux is also in Linux. So let's take a quick tour through that. Now, it's a little premature to get heavy into operating system course details. That's CS 281, and so I don't expect you guys to be experts at all the stuff we're about to cover, but I want you to at least have a passing familiarity with some of these concepts, because they're pretty important and they are at the heart of everything we do with computing these days. So some of the things you find in Linux and Android Linux are core abstractions for managing the hardware devices, hardware resources in a modern operating environment. So the key things we're going to talk about virtual memory, processes, and threads. So virtual memory is basically a way of giving application developers the illusion they have a lot more memory than there is physical memory on the device. Most devices, even with today's absurdly bloated amounts of memory, like 8 gig or 4 gig of RAM, you can still pack a lot more stuff with all the different things that have to run than there is physical memory. So there's something called virtual memory. And virtual memory basically does two things. It allows the illusion that you have much more memory on your device than you really have, because it uses backing store, which is slower, less expensive memory, in order to store things when they're not actually being actively accessed by the processor. So that's one thing virtual memory does. And the second thing that virtual memory does is it allows you to physically isolate memory in one application from memory in another application, so that you can't accidentally read or write to the memory that you don't have access to. And the main motivation, of course, is security, because you don't want people tampering with things that they shouldn't have access to, but also just robustness. You don't want scribbling over parts of memory address space and then corrupting the state of the program. So that's what virtual memory is all about, and you can find out more about it here. When you take the OS course, you'll learn more about it. The second thing, and this is actually not unrelated to virtual memory, that are important in operating systems are things called processes. So a process is basically a unit of resource allocation and protection, and different permissions, different resources, different memory segments, and so on can be shielded from each other by allocating them in separate processes. So a process is basically something that you can create or spawn as an application developer or a system developer. And in fact, when you run an app in the Android environment, it runs in the context of a process. Now, those things have been around for 40, 50 years at this point, and you can learn more about them here. More fine-grained than the process is something called the thread. And a process can have one or more threads. And a thread is basically a unit of computation or a way of executing streams of instructions in the context of a process. And one process can actually have multiple threads. And we'll see lots of examples later of how this works. Let's see. And these threads are then mapped to run on the underlying processing cores. This is a metaphor for a core, right? We have multi-core. I'm not making any statements about whether Apple has good cores or not, but they do provide a good metaphor. So those are some things that you'll find in Android Linux. This is what you'd find in Linux. This is what you find in Android Linux. You'll also find a pot of protocol stacks, which are used to access the outside world. Of course, everybody wants to go and be on Facebook or Twitter or do browse the internet. Whatever you want to do, you need to use the internet protocols. There's internet protocol stacks that are there, very sophisticated. And then there's also something called a device driver framework. So anybody think of any of the kinds of devices that you might want to connect to your smartphone? So headphones, yeah, great example, headphones. You want to plug your headphones in. Other devices which are not so obvious but are really important, of course, would be the touchscreen driver, the thing that manages the touchscreen. That's obviously something that's a device. And speakers, the microphone, the radio. There's all kinds of crazy things that are going to be accessible through the operating system. And this thing called a device driver framework gives ways of accessing those, either a character at a time or a chunk of bytes at a time. So chunk of bytes at a time would be things like flash memory or various other kinds of solid state drives. Character devices would be things like network interfaces. You have to read a character at a time. All right, so those are just common things. Again, this is not an OS class, but you've got like the first month of an OS class in 30 seconds, right? The other set of things that Android provides are Android-specific enhancements to the operating system. So for example, they have a really cool driver that handles communication between processes, because one of the important things you do a lot in Android is talk between different processes to get things done. You have system processes, and you have application user processes, and application developers can write processes, and they have to communicate back and forth. And there's a bunch of services that are provided for you by the underlying system services that Android provides, and so on. So to make this all work well and efficiently, they have something called the binder driver. And it's basically an inter-process communication mechanism for sending data back and forth between the different processes. Yeah? So a driver is just a bunch of system software that knows how to control hardware devices. So if you have a touch screen on your computer, right? I mean, obviously you have a touch screen on your smartphone, or you have a network. You have a transceiver. You have a Wi-Fi piece of hardware. Or you've got Bluetooth, right? The hardware that is the actual physical hardware then has a thing called a device driver, which is a piece of software that runs in the context of the operating system to talk to that piece of hardware. And it's very low level and nasty and horrible, and you should be very happy it's not 1972 or something, because that's the kind of thing we'd be doing in this course if we were learning about that stuff, because that's what they did back then. So there's ways of communicating between high-performance inter-process communication. There's ways of sharing memory between address spaces, which is another way of trying to optimize communication so you don't have to copy the data. You can put it in shared memory and pass pointers or references to that memory back and forth. There's some really cool support for power management that allows the applications or system services to control whether the device is able to sleep or not. As a general rule of thumb, you usually want the device to be able to sleep when it's not being used. In fact, on most of these things, if you don't use it for about 15 seconds, it blanks the screen, right? Because screen draws a lot of power. But there's every once in a while you want something that will actually keep going even when you don't want the device to shut down, like when someone does a phone call, right? While you're talking on the phone, if you haven't touched the computer for a while or the interface, you don't want the thing to shut down. So there's things called wake locks, and that's part of the power management features that Android has. And there are all kinds of ways of trying to control how power is managed. Big issue in modern mobile computing is trying to deal with power issues. Another interesting thing they call the low memory killer. Sounds kind of sinister. Sounds like you want to have, CSI, low power killer, right? Something like that. And what it does is when memory starts to be running low on your device, it goes around and it finds applications that it deems to be doing unimportant things, and it euthanizes them. It's very heartless, right? It just shuts stuff down. When we talk more about Android's lifecycle model, you'll learn why this is important. All right, so those are some of the kernel level things. Again, you don't have to be an expert on this. You just have to sort of know that there are kernel level things that are important and roughly what they do. The next thing we're going to talk about is the hardware abstraction layer, or the HAL. Does anybody know what this is? That's HAL, right? And HAL 9000. I told you about, did I tell you this? This is a good little piece of trivia to know. If you want to impress especially your parents, people your parents' generation, because they probably watch this. So if you go and watch 2001 Space Odyssey, which is where HAL is from, then you'll find out that HAL is basically IBM++, right? So they incremented every letter, right? Pretty cool. So that's like science fiction geek trivia. Now this is just geek trivia. Okay, so if you know what Windows NT is, Windows NT is the operating system technology that underlies Windows. And it was developed by a guy named Dave Cutler, who prior to coming to Microsoft had been the chief architect of VMS at DEC. And so when he went to Microsoft, he invented Windows NT, which was basically VMS++. So that's serious geek trivia, right? This will make you a big hit at like Comic-Con or something like that. But if you're at CES, then you'll know some like really cool trivia there. So that's the hardware abstraction layer history. The hardware abstraction layer in Android is there to separate out some concerns. For example, it separates out Android's platform logic, the software that Android's platform provides up to the applications, from the hardware, as well as from the operating system. And so this is really weird. It provides a user space library written in C and C++ for accessing devices that live in the operating system kernel, which seems odd because usually devices that live in the operating system kernel are actually accessed via operating system kernel level drivers that live in kernel space. Whereas what we find in the HAL is actually living in user space. And we'll talk about why that is in a second. Yeah? What's the kernel? A kernel is everything we just talked about. So everything we just talked about with Android. What were some things we just talked about with Android?
Like drivers and stuff.
Drivers, network protocol stack, processes, threads, virtual memory, binder driver, low memory killer. Those are all things that run in the OS kernel. And that's typically a protected address space that has special access to regions of memory and instructions that the hardware can run. And so it's the part that makes sure, for example, that makes sure that you don't have one application accessing information it shouldn't have access to because it has the wrong permissions. So the kernel is kind of like it's like a traffic cop that keeps track of information flowing around inside of an operating environment. So everything we just talked about, all that other stuff was in the OS kernel. So the hardware abstraction layer basically provides an interface to the hardware drivers. And they put it in user space for some interesting reasons. Part of the reasons were technical. So a lot of the devices that you find, a lot of the hardware that you find in a mobile phone are not the kind of thing people up to this point had ever expected to find in a Linux environment. So for example, a Linux environment that you would have for your desktop or laptop probably doesn't have a radio in it, right? Because you're not making phone calls with it. Might have Wi-Fi, but it doesn't have a cellular radio. Likewise, there's various kinds of things, cameras and other kind of stuff. You probably don't have really high resolution megapixel camera in your laptop, whereas you probably do on your smartphone. So there's a bunch of interfaces that are not actually part of the standard Linux kernel that they wanted to have people have a standard interface to that were not provided the standard interface in the traditional kernel interfaces. But that's actually just the cover story. The real reason was that the Linux environment requires people who provide operating system drivers to release them in open source form because of the way that they license kernel modules in Linux, because of the use of the GNU public license. The variant of the GNU public license that's used for Linux is very, very liberal in the sense that everybody has to have access to everything. Free as in freedom, as Richard Stallman likes to say. So as a consequence, if they had put all this stuff into the OS kernel drivers, then everybody who was a manufacturer of Android devices would have had to have released all their source code for their touchscreen drivers and all kinds of other stuff in open source form. And a lot of people aren't comfortable doing that because that's their competitive advantage. That's how they differentiate themselves. That's how LG separates themselves from Samsung, separates themselves from Motorola, separates themselves from Huawei or whoever. And so they were uncomfortable with that. So by having the user level drivers, having the drivers be put in user level for the hardware abstraction layer, allowed them to circumvent the overly liberal licensing model, overly liberal is in quotes, of course, that are there in GNU. It's a little beyond the scope of this class to talk about open source licensing models, but at some point when you get, if you go further along in computer science and you get to the upper division CS 297 course, it's a seminar course that's kind of a projects course where we talk about a lot of broadening topics, and one of the topics we'll cover there is open source, which is kind of cool, and licensing issues are a big deal there. All right, next topic, this is actually some recap, so I'll go through this very quickly, is Java virtual machine. So there's a runtime environment that has a virtual machine. You probably recall from the first day or so of class we talked about a virtual machine being a hosted environment for executing bytecode in a managed way. And so in Android, like in most virtual machines, the unit of the execution and creation of bytecode containers is the process, which we just talked about, which is part of the kernel. And the virtual machine environment abstracts away a lot of the details of the underlying hardware. So you don't have to know or care that you're running on one processor or one chipset or another. And Android applications typically run in their own process inside their own VM instance. So if you're the Android browser application, for example, then your browser is going to run on top of a bunch of other things that are out of the box, part of the Android environment. What's interesting about Android, and this triggered years worth of expensive litigation between Oracle and Google, is that while they use Java to write the bulk of the applications in Android, they don't actually use the Java virtual machine TM as the underlying virtual machine. Instead, they write their own virtual machine called Dalvik. Dalvik is a charming little village in Iceland, which is where the guy who wrote the original virtual machine was from. So he called it Dalvik. And it's a little different from a standard Java virtual machine. I don't have time to go into all the nuances. If you take a look, there's a bunch of cool videos you can learn about the internals of Dalvik to see how it compares and contrasts. I will not hold you responsible for that. There are programs that will take Java classes and turn them into Android-specific bytecode formats so they can run on an Android environment. There's also a cool thing called a Justintime compiler. Just-in-time compiler will take a look at the code as it's executing and see what parts of the bytecode is run frequently, and then it will decide automatically to compile that into binary form and be able to execute it natively. Yeah?
What prevents someone from just giving Java a compiler and having it turn into binary?
Oh, so the question is, what prevents you from turning Java code into to a binary? Well, in fact, that's what's called the Android runtime, which is the new virtual machine format that Google is moving towards, which you can learn about if you watch this video. And what they have, this is what you're actually talking about, they have something they call an ahead-of-time compiler. So instead of a just-in-time compiler, ART, as it's called, Android runtime, has an ahead-of-time compiler, which tries as much as the Java semantics allow, which is the kicker, to try to convert the Java source code into binary, although there are certain semantics of Java having to do with verification of certain things and late binding and so on, where you can't entirely compile it all away at compile time, but you can get pretty close. So they have this thing called an ahead-of-time compiler. You can read more about all that stuff here. And they also have better garbage collection as well. In the last couple seconds here, the virtual machines, whether it's Dalvik or ART or whatever, they implement all the concurrent programming language features that they support in Java. And we'll cover more of those as we get a little further along in the course. OK, so at this point, a couple things. We are not going to have a quiz on Wednesday because we just didn't cover enough stuff. So this stuff that we cover here we'll cover next quiz, which will be a week from Wednesday. And